So x equals 0 is the y-axis. That means I'm going to reflect this initial arm across this line. This is actually, whoops. Yeah, that's right. X equals 0 is the y-axis. I'm going to reflect it this way. This is horizontal, which is weird. A horizontal reflection is across the y-axis, which is x equals 0. It requires a bit of thought. You can easily psych yourself out there. But here's the point. If the terminal arm was originally in quadrant 1 and I reflect it across that line, it's going to be in quadrant 2. And we know the reference angle is still going to be 38 degrees. That's what we learned right at the beginning. So all I have to do is draw a terminal arm in quadrant 2 with a reference angle of 38 degrees. And we're back in yesterday's mode where we have to find the rotation angle, 180 minus 38 degrees. 142? Thank you. What if I reflect, are we done with that question? Okay. What if I reflect an angle in standard position is 135 degrees. What if I reflect the terminal arm in the y-axis? So the difference here between this question and the one we just did, I'm not getting you to draw it. Okay? But I don't want you to do it without drawing it. I want you to draw it. I see a lot of you doing this right now. You're going, if you can figure it out in your head, that's great. I can't reliably do that. If I did that, if I were marking an exam or making a key for an exam, and I saw this question and I worked it out in my head, I would want to do it on paper just to make sure I put the right thing in the key. So in the y-axis, well, here's the diagram. The terminal arm is at 135 degrees, which I believe is 45 degrees between the axes in quadrant 2. So the terminal arm is here with a reference angle of 45 degrees. I can't judge 45-degree angles when I'm that close for some reason. That's 45 degrees. This is 135 degrees. This is the starting point for all of these. If I reflect that in the y-axis, which quadrant will it be in? 1. In the y-axis, which is this vertical line, what's going to happen is it's going to be over here now. Straighten that up. So what's happened is I've gone across this line. I've gone across this line to the other side. Well, that means still 45 degrees. The answer to the question is the rotation angle is 45 degrees. In the x-axis, if I reflect this original one, this is original, and I reflect it in the x-axis, which is y equals 0, which is this line, then it will go from quadrant 2 to quadrant 3. And I will have a terminal arm in quadrant 3 with a reference angle of 45 degrees. And everybody should be able to figure out what that rotation angle is by saying it must be 180 plus 45, which is 225. If I reflect it in the y-axis and then in the x-axis, so if you're watching this on video, you can't see my arm movements, but here's the terminal arm in quadrant 2. I reflect it in the y-axis. I reflect it in the x-axis. It's going to be in the diagonally opposite quadrant. It's going to be down in quadrant 4. I would go so far as to say I think most of you should be able to figure out that's 315 degrees without drawing it. But just to be complete, we draw it. We are dealing with a 45-degree reference angle in that quadrant, quadrant 4. The rotation angle is how many degrees all the way around from 0, which would be 360 minus 45. Done. All right. Now the heavy lifting. Okay? Trigonometric ratios of special angles. So in trigonometry, we encounter certain angles more frequently than we encounter other angles. And I know that everything I'm about to show you is on your handout, but I want you focusing your attention up here, please. So special angles are angles that are multiples of 30 or 45 degrees. I want you to notice that if I start looking at multiples of 30, I'm going to hit 60 degrees and I'm going to hit 90. So often what we say is special angles are multiples of 30, 45, and 60, and 90. But 30 covers a lot of that. So when I take a look at this diagram, and I know your diagram has more information, but I want you to focus up here. I want you to notice that each of these green dots is separated by 30 degrees. Right? If I wanted to, and this diagram gets more complicated in Math 30, I could demonstrate to you that we get 3 equal pieces of that corner, and that corner is 90 degrees, as is every corner that's done correctly, and a third of 90 is 30. So each of those is 30 degrees. Each of those green dots is 30 degrees away from the next green dot. So this is 30, the next one is 2 times 30, the next one is 3 times 30, 4 times 30, 5 times 30, 6 times 30, 7 times. We're just adding 30 degrees each time. And these are very important positions for you to be able to locate. Okay? 240, 270, 300, 330. What about these ones? And we're back to 360. What about those ones? Those are not multiples of 30. What are they multiples of?
45.
45. So the first one's 45 away from 0, then 90, but we already have 90. Add 45 to 90, we get 135. Add 45 to 135, you get 180, but we have that. 180 plus 45 is 225, plus 45 is 270, plus 45 is 315, and then we're back to 360. So to begin with, you need to visually be able to locate these angles. And I would ask you to really give some careful thought here to the spacing of those dots. Specifically, I want you to notice that this arc length here is twice this arc length. In other words, those 3 dots, this dot here is at the 45-degree angle. It's halfway, angularly speaking, between the 2 axes. And then the 30 and 60 are relatively close to it. They're only 15 degrees off. And if you don't draw this well, it may cause problems for you in solving certain questions. Okay, warm up. I have 2 triangles here. I want you to notice that each of these triangles contains a right angle, and I want you to confirm that each of the triangles' angles add up to 180 degrees. I mean, I hope many of you would say, since this is a right angle, the other 2 angles have to add up to 90. Okay. What's interesting about these triangles is they contain our special angles. Okay. So, the hypotenuse of each of these is 2. What is the exact value of all of the other sides? That's the warm-up. How can we find the exact value of these 2 sides? I'm going to start with the triangle on the left. How can we determine the exact value of that side and the exact value of that side? I realize that some of you may be hung up on the exact value. Forget about that for a second. How can you determine how long those sides are if the hypotenuse is 2? Does anybody have any ideas? Claire?
Use the sine or cosine formulas, maybe?
Well, you could. Okay, let me show you what would happen, and I do not want you to write this down. What would happen is, I love that you said that actually, is you would say, I'm going to focus my attention on this angle, and I'm going to call this the opposite side. And again, you're not writing this down because this is not going to solve the problem. And you'll see why in just a second. I could write sine of 45 degrees equals the opposite side whose length I'm after over 2. Nobody has ever said what you just said, Claire. I don't remember anybody ever saying it. I'm glad you did, though. Can we use this to calculate the length of the opposite side? Yes, we could. Let me show you what we're going to get. A very elementary equation to solve. We're going to take 2 times the sine of 45. Make sure I'm in degrees. 2 sine 45. Except I want an exact value. I don't want decimals. I can't get a fraction out of that. And you know why I can't get a fraction? Because it's not a rational number. So we could use what you suggested, Claire, to find the value of each of those sides. But unfortunately, we can't find the exact value. This is the point we need to understand today. This is what we're after. If we knew the exact value of sine of 45, we could do it that way. And that's what the objective is. What is the exact value of sine of 45? I'm not going to tell you what it is. I know what it is. Okay? It's a number. I can tell you the exact value of it without using decimals. So, unfortunately, it doesn't work. Not for the conditions that I've set, which is we want an exact value. So what other tools do we have? Owen?
Since both legs are the same length, you could use Pythagoras.
Sure. And what I'm going to do, and I think this is where you're going with this, I'm going to introduce an unknown. I don't really want to use x, okay? I'm just going to use L for leg. Owen has recognized that since these two angles are equal, this is an isosceles triangle, which means those two highlighted sides are equal. And now I can use the Pythagorean theorem because I only have one unknown. I can write hypotenuse squared equals other side squared plus other side squared. I get 4 equals 2L squared. I mean, pizza plus pizza is 2 pizzas. L squared plus L squared is 2L squareds. I can divide both sides by 2. When I do that, what I'm going to get is 2 equals L squared. L is equal to the square root of 2. Exactly the square root of 2. That's the square root of 2. I love that you asked that you answered the question that way because nobody ever has, and I never thought of doing it that way. You know how to do this math, you just don't know how to get an exact value yet. Okay. So that's root 2, which means, and I hope this is our work. We're writing this down, right? And then we can say those two sides are each root 2. And one way or another, everybody, you need to burn into your brain this triangle. You need to know that when you have a 45, 45, 90-degree triangle, that if the hypotenuse is 2, each of the other sides is root 2. Now, in other words, this triangle, and the one we're going to do, they are the key to solving any problems that we work on today. Now, this next one is more challenging. And I always ask people to see if you can come up with a way to do it. And it must be as an exact value, so we can't just use SOHCAHTOA. And over the years, maybe me asking 30, 40 times, does anybody have any ideas? There have been 4 or 5 people that have come up with a way to determine, first of all, the length of the yellow side. And you can determine the length of the yellow side in your head somehow, if you think of it right. I don't know if anybody here is going to get it. Requires zero calculation on your calculator. It's just when you see it, you know it. And I have to say, it's something I never would have thought of. I know it because somebody taught it to me. Yep.
It's not L is yellow and then the tall one is 2L. Yeah, like 2.
No. Are you saying that the height of this is twice this? Oh, okay. It's not. By the way, I put this blue line in the wrong place. I meant to put it here. These are the two sides we want. But are you saying that this is twice as tall as it is wide? It isn't, actually. It's about 1.73 times as tall. About. So I apologize. I put the blue one in the wrong place. We want to find the lengths of these two. I'm telling you, you should be able to figure, not should be, it's possible to figure out the yellow length just by looking at it. Here's my hint. What if I take this triangle and I clone it and I reflect it horizontally and oh, interesting. Oh, because I've rotated it. And I reflect it horizontally, which is vertically because it's sideways. Don't worry about it. And I'm going to have to rotate it. Nope. Man. That's messing with me. Flip, left, right. There we go. What if I clone this and rotate it and I put it right here? Does that help you figure out what the length of that yellow side is? You know? It's 1. Why is that?
Because then it creates an equilateral triangle.
Perfect. If I do that, this is 60 degrees. This up here is 30. This must be 30. We've got a 60, 60, 60 degree triangle, which is equilateral, which means all three sides are equal, which means the big base of that triangle has to be 2. If this is 2, this has to be 2, and that has to be 2. But these two sides, these two small bases here are equal, so that yellow one must be 1. And this is something that you will recognize from now on. I want to go back to where we were. That anytime you have, there we go. Anytime you have a triangle with a 30-degree angle in it, the shortest side will always be 1/2 of the hypotenuse. Always. Do me a favor, and this is just off the cuff. I wasn't planning on getting you to do this, but I want you to do it and see if it turns on any lights in any of your heads. Take your calculator and take the sine of 30 degrees. You get 0.5. Sine is opposite over hypotenuse. Opposite the 30 degrees is 1, the hypotenuse is 2. 1 over 2 is 0.5. If this were 20, this would have to be 10, because the sine of 30 degrees is 0.5. Anyway, now that we know that that's 1, you can certainly figure out what this is using the Pythagorean theorem. And again, the letter doesn't mean anything. I'm going to stick with L. I can write 2 squared equals L squared plus 1 squared, which gives me 4 equals L squared plus 1. I subtract 1 from both sides and get L squared equals 3. So L equals the square root of 3. So this is root 3. Did I take attendance? Just a second here. Oh yeah, I did. Oh, Lucas. Remember when you said that the blue was twice the base? And I said, no, it's actually about 1.73. Can you calculate the square root of 3? 1.73-ish, yeah? So, okay, where are we going with this? Where we're at right now is I'm telling you, by hook or by crook, you need to know these two triangles. They are the key that will unlock the door to many problems we do. Now, at the beginning of the class, I said to you, you need to be able to determine the exact value of things like cosine of 210 and all that. Well, it's based on these triangles. These are exact values. So let's take a look at the question. What is the exact value of the sine of 30 without a calculator? What you do is you construct this triangle that I'm looking at here on the right. You look at the 30-degree angle, and you say sine of 30 is opposite, which is 1, over hypotenuse, which is 2. The exact value, we'll see it tomorrow, the exact value of sine of 30 degrees is 1/2. So we put that in the list. What is the cosine of 30? Well, you look at the 30-degree angle. You say to yourself that cosine is adjacent over hypotenuse, right? When I'm looking here, this is the opposite, this is the adjacent, and this is the hypotenuse. So the cosine of 30 is root 3, which is the adjacent, over 2. Do me a favor, take your calculator, figure out the square root of 3 divided by 2. You have to close the brackets on the square root. Or if you're like me, old school, I go equals, divided by 2, equals that number. What's the cosine of 30? That number. They're the same. Tangent of 30. Well, go to the triangle. Tangent is opposite over adjacent. Opposite is 1. Adjacent is root 3. It's 1 over root 3. Now we have a little bit of business before we go on. And there's a reason for what I'm about to tell you. There's a reason why it's true, but we will not learn the true reason until later. Okay? I just need to show this to you. Do me a favor, do the same thing here that we did with cosine of 30. Take the tangent of 30 and look at that number on your calculator. And also figure out on your calculator what 1 divided by root 3 is. So tangent of 30 degrees. So I can't change this. Can't change it to a fraction. It's not an exact value. It's an irrational number. As an exact value, it's 1 divided by the square root of 3. You agree? I would like you now to figure out what the square root of 3 divided by 3 is. Same number. What I'm telling you, everybody, and we don't need to worry about why, we'll learn this later in another unit, is that I don't care. Root 2 divided by 2 is the same as 1 over root 2. 1 over root 7 is the same as root 7 over 7. And sometimes we will see it written as 1 over root 3 here. Sometimes it will be root 3 over 3. Sine of 60. I'm going to pick up the pace. You look at this triangle, of course, what happens now, everybody, is we are not focusing on the 30, we're focusing on the 60, which makes this the opposite and this the adjacent. So sine of 60 will be opposite, which is root 3, over hypotenuse, which is 2. It's no coincidence that these are equal. because I go from the 30-degree angle to the 60, the opposite and the adjacent switch places. Cosine of 60 is going to be adjacent over hypotenuse when you're looking at the 60. But when I look at the 60, adjacent is 1, hypotenuse is 2. Tangent of 60 is going to be opposite, which is root 3, over adjacent, which is 1. So that's just root 3. 45, sine of 45, I need you to look at your triangle with the 45. Opposite 45 degrees is root 2. Adjacent, hypotenuse is 2. Cosine, adjacent is root 2. Hypotenuse is 2. Could we write these this way? You might wonder why that would ever happen. There's a reason in Math 30 that it would happen that way. They're the same. Just like root 3 over 3 is the same as 1 over root 3, root 2 over 2 is the same as 1 over root 2. Tangent of 45 is 1. Opposite over adjacent, look at your 45-degree angle. Opposite is root 2. Yeah, adjacent's root 2. Root 2 over root 2 is 1. So from now on, and it's going to get a little more complicated, if I say, what is the cosine of 60 degrees, you should be able to think about it and go, it's 1/2. What is the sine of 60 degrees? Root 3 over 2. I know it seems a little weird, and you might be sitting there thinking, man, is this just because there's some old school people making decisions about what people should know about math? No calculators? No. It has uses. Okay? Use your calculator to find the value of sine of 0. What's the sine of 0? Which is kind of weird. 0 degrees. One? No, sorry, 0. 0? What is the cosine of 0? 1. Sine of 90 is 1. Cosine of 90 is 0. We are going to learn why that's the case tomorrow. Okay? So all this exact value stuff extends beyond 30, 60, 45, but we're going to do more of it tomorrow. All right, examples. Next page, I think. The pendulum of a metronome arm is 10 centimeters long, or the arm is 10 centimeters long. You can see here, I don't know how well it printed on yours, but there it is in one position, and there it is in another position. And it goes from 45 degrees to 135 degrees. I apologize if you're watching this video. I've been muted for a while and I didn't realize it. If you look at the triangle in green, adjacent to 45 is root 2 over hypotenuse, which is 2. It's root 2 over 2 for cosine. So what we end up with here is b is equal to 15 times root 2 over 2. This is math 20. This is not math 20-3. It's not even math 10c. We have to carry that expression, 15 root 2 over 2, in the next step. When I take a look at this triangle on the right, and I look at the 60 degrees, in terms of the 60 degrees, this is opposite, and this is the hypotenuse now. That number we just found, which was the adjacent side on one triangle, becomes the hypotenuse on the next one. So, let's see. We have hypotenuse, opposite. I guess that's going to be sine. So I write sine of 60 equals opposite. Oh, we're finally getting to the answer. Divided by the hypotenuse, which we found is 15 root 2 over 2. Don't let this beast in brackets scare you. It's just a number. We don't want it as a decimal, but it's just a number. Just leave it the way it is. What that tells me now is that x will be equal to 15 root 2 over 2 times sine of 60. Well, what's sine of 60? Figure it out. Go to the triangle that has the 60-degree angle in it and look at the opposite and the hypotenuse, because sine is opposite over hypotenuse. Root 3 over 2. I mean, sooner or later, everybody, you're going to know sine of 60 is root 3 over 2. Sine of 30 is 1/2. You will get it. But when I go back and I look at that 60-30 degree triangle, sine of 60, opposite is here, hypotenuse is here, it's root 3 over 2. So we're going to have root 3 over 2. Now, I can multiply the 2 times the 2 on the bottom and get a 15 on the top, a 4 on the bottom. You know, sometimes things just don't line up perfectly. You haven't been taught this yet. But since that 2 is under the radical and the 3 is under the radical, I can multiply them together under the radical. Okay? I can take numbers like this 2 and this 2 and multiply them together because they're not under radicals. And I can take numbers like the 2 on the top and the 3 on the top and multiply them together because they are under radicals. Now, that's the exact value. If we wanted a decimal value, we could figure it out, but we don't. Final question. What is the exact value of this? I mean, you could certainly throw that into your calculator and tell me a decimal, but that's not what I want. I like the fact that many of you are flipping back right away because you're trying to determine what is the cosine of 30 degrees. I believe it's root 3 over 2. No good. Here's my thinking though, guys, just so you know. This is always 2. Oh, wait, this is 1, because if I flip it over, I get that equilateral triangle. Oh yeah, I remember, this is root 3. You will remember it after a while. Cosine of 30 is root 3 over 2, adjacent over hypotenuse. Sine of 45, how many of you know sine of 45 is root 2 over 2? I mean, how many times do we have to look at that triangle before you go, yeah, it's root 2 over 2? This is the exact value. Unfortunately, we do not like fractions unless they're put together. So I can rewrite this 1 as 2 over 2, and now I have a common denominator and I can put it together. 2 minus root 3 minus root 2 over 2. And for the sake of being open with you, I think you need to understand that I can give this to you as an exam question. I wouldn't give it to you as a multiple choice question, because if this is one of the choices, you can just put 1 minus cos 30 minus cos 40 sine 45 in your calculator and then figure out A, B, C, and D and find out which one matches. But I could say that this is equal to A minus root B minus root C over D. What are the values of A, B, C, and D? Again, we're going to extend this tomorrow. I have 4 problems, I believe, on the next page that I want you to do.
There's 5.
There's 5? Okay, so I have 5 problems on the next page, and it says 5 on yours then, yeah. So that's what you're working on for tomorrow. You have about 20 minutes left. I'm also going to hand back your exams.